So having figured out what the direction of a gradient vector tells us, it's perpendicular to the contours and it points in some direction of increase of the function. So it's going to point uphill on the graph. It's going to show us how to go uphill on the graph, if you like. But the question next is, what about its magnitude? What does the magnitude of a gradient vector tell me? Because it looks like the magnitude can vary pretty considerably, right? For this particular surface, my gradient vectors as I get points that are close to the origin look like they're pretty short. And the further out that I get, my gradient vectors seem like they get a lot longer. And so it's valid to ask, like, what feature of f is that gradient vector actually capturing for us? And you might even, just based on this picture that we're seeing here, hazard a guess that somehow the longer gradient vectors are communicating something about a steeper surface to the graph. Because here toward the origin, we have a very sort of gradually sloped paraboloid, and the further out that we get, the steeper the slopes on that paraboloid get. And you wouldn't be wrong, but we want to kind of understand that from the perspective of directional derivatives that we kind of started the day with today. And so this next activity we're just going to kind of talk through together rather than have you work through this in your teams today. And then after that we'll have one more thing to do to wrap things up today. So why is it that the gradient does what it does? Well, one of the reasons that the gradient does what it does is because, once again, of this directional derivative formula. This is our sort of engine for pretty much everything that we're doing today, is this directional derivative formula. Back up here. Oops, where is it? Nope, it's over here. So the directional derivative formula told us that to find a directional derivative, what we end up needing to do is take the dot product of the gradient vector with a unit vector that points in the direction that we're interested in. Right? So gradient vector dotted with unit direction. That gives us the directional derivative. And so because that is a dot product, it carries geometric information about both the lengths and the angles of the gradient vector and the direction vector, respectively, right? Because that's what dot product can measure in geometry. It measures information about lengths and it measures information about angles. And fortunately for us, the direction vector here is a unit vector to begin with by assumption, right? And so that means that the magnitude of that v vector, the v hat vector here, is just equal to 1 in this formula. And so only the magnitude of the gradient will be expressed, if you like, as part of the directional derivative. So let's remember real quickly what the geometric definition of the dot product of two vectors was when we were first introduced to dot product a while back. At the time, we were interested in using operations to do geometry with vectors in 2 space, 3 space, any number of space. And what we said back then was that the dot product of two vectors measures the product of their magnitudes multiplied by the cosine of the angle that the two vectors make, right? So the dot product of v and w is the product of the magnitudes of v and w multiplied by the cosine of the angle that v and w make. And so as a direct consequence of that, we saw, for example, that vectors that are exactly parallel to one another, like this, will maximize the value of the dot product of any two vectors of their given lengths, right? Because the angle between them is 0, and the cosine of 0 attains the maximum value for cosine, which is 1. That when two vectors are anti-parallel to one another, the dot product realizes the largest negative value that the dot product can have, which is the opposite of the product of the magnitudes, because the cosine of a 180-degree angle is -1. But probably most saliently, we can use the dot product to tell us when a pair of vectors are perpendicular, because at that point the dot product must be 0, regardless of the magnitudes of those vectors, because the cosine of a 90-degree angle is equal to 0. So the biggest use case for dot products for us in geometry is to give us a way to detect when two vectors are perpendicular to one another. And so given that perpendicularity has sort of risen its ugly head as part of our gradient vector discussion already, it makes sense to go back to this idea of directional derivative, the fact that it's defined as a dot product, and mine that definition for some geometric information. So what can we tell about the gradient vector based on the fact that the derivative, the directional derivative, is the dot product of the gradient vector with a cosine, with a unit vector in the direction that we're interested in. Right? So this activity just asks to explain why the directional derivative is just equal to the magnitude of the gradient vector multiplied by the cosine of the angle that the gradient makes with the direction that we're interested in. And this just follows from the geometric definition of dot product. And that's because again, the directional derivative, du of f, is, by its definition, by our formula, it is a dot product. And it's a dot product with a unit vector. So that unit vector has a magnitude of 1. So I'll just sort of follow what they did here. So the directional derivative in the u direction of a function f at x naught, y naught is just equal to the dot product of the gradient, nabla f at x naught, y naught. And the dot product is happening with a unit vector, f, u. And using the geometric definition, that's equal to the product of the magnitudes of these two multiplied by the cosine of the angle. So I'll put a magnitude around the gradient, and I'll put a magnitude around my unit vector over here, and then I'll stick a cosine theta on the end of it. And so we're sort of up to here in the process. And then we just have to remind ourselves, right, that the magnitude of a unit vector, just by definition of what a unit vector is just equal to 1. And so because that magnitude of u is equal to 1, all we have left, the only thing that survives, is the magnitude of the gradient multiplied by the cosine of the angle that it makes with the direction that we're interested in the directional derivative. Okay, so that was part A, is just to make that geometric connection to what we know about how dot products work. And so in part B, the question is, explain why an angle of 0 degrees makes this quantity as large as possible. And that's, again, goes directly back to the discussion that we just had, right? That the dot product between two vectors is at its largest when those two vectors are parallel to one another. They make an angle of 0 degrees. And it's because at an angle of 0 degrees, the value of the cosine is maximized, right? The value of the cosine is equal to 1, and that's the largest value that a cosine can have. So that's the conclusion, is that if we walk in the direction of the gradient vector, not only are we going uphill, we are going uphill as rapidly as we can at that point, right? It has the largest directional derivative among any direction that we could have chosen at that point. So the directional, it's as large as possible because the cosine of theta is as large as possible. Because at an angle of 0, the cosine has its largest value, namely +1. Yeah. And so in part C, when theta is 0, in what direction does the unit vector point relative to the gradient of f? And then what does this tell us about the direction of greatest increase? Again, you just answered that question, right? That the gradient actually points in the direction of greatest increase. So the largest directional derivative, i.e. the steepest slope, occurs when we select a direction that is parallel to the gradient at the point. So the gradient vector itself points in the direction along which f increases the most rapidly. So the steepest uphill is found in the direction of the gradient. And again, we can kind of get that sense from this diagram, right? That In this particular paraboloid, it looks like my gradient vectors are always pointing directly away from the origin. And if I'm trying to climb up out of this bowl as quickly as possible, I'm going to climb up in a direction that goes away from the origin as quickly as possible. So it points in the direction of the most rapid increase of our function. So it points not only uphill, but literally as uphill as possible at each given point. Okay. Let me not lose my place here. So here's an interesting question. What direction would be the direction of greatest decrease? So the gradient only knows how to point uphill. How could we figure out how to point downhill? Not only downhill, but as rapidly downhill as possible. So if I took my gradient and I multiplied it by -1, I'd be moving in the opposite direction of the gradient, right? Exactly opposite to the gradient. And if I do that, I'm moving in a direction that makes an angle of 180 degrees with the gradient, right? And so the cosine is going to be equal to -1 at that point, which is the largest negative value that the cosine of any angle can have. So the opposite direction of the gradient, in other words, I'm getting too lazy to use Hypatia. I'm just going to Unicode this one. Minus gradient of f will point in the direction of most rapid decrease, since it makes a 180-degree angle with the gradient, and so the cosine takes its largest negative value. Right. So if I want to go uphill as quickly as possible, I follow the gradient. If I want to go downhill as quickly as possible, I find the gradient and then I walk exactly in the opposite direction as the gradient was pointing. This, by the way, is something that nature does a lot. Like when I say nature, I mean the laws of the physical universe do this kind of thing pretty frequently, because very often there are physical situations where nature tries to minimize the amount of energy that's expended to do something. Like when you hear, for example, that electricity follows the path of least resistance to get to where it's going. It does that by following the opposite of the gradient vector of some energy function, right? It wants to dissipate its energy as quickly as possible, so it wants to go down the energy surface as quickly as possible, and so it follows the opposite of the gradient. So there are a lot of places in physics and in the sciences where we find that this principle of trying to figure out how to either increase or decrease as rapidly as possible is something that is physically interesting. And when it is, you'll find that the gradient is used to do that. The gradient is also valuable in a process called gradient descent, which is a way to try and find the tops or bottoms of mountains or valleys for a multivariable function. It's like I have a contour map and I'm trying to get to the top of a mountain. And so what I do is I look and see, well, where am I? What contour am I on? And then I'm just going to walk perpendicular to that contour and then check again. All right, what contour am I on now? All right, I'll walk perpendicular to that contour again. And if I keep doing that, eventually I'll arrive at a critical point, which we hope then is the top of a mountain, which at least locally going to be something that looks like the top of the mountain. The last piece of this.
Well, okay, I don't know if this is what you meant, but at the origin, there's no direction. So
in the example we looked at earlier in that contour plot, yeah, it happened at the origin. Let me bring that contour plot back up. Because, yeah, that's exactly the situation that they want to bring to mind here. Nope, I just want to load up. And that was, directional derivative. Now we'll do this one, because we did this one before. Slide that out of the way. Right. So anytime that the gradient vector is 0, there is no direction of greatest increase. There's no direction of greatest decrease. And so that can be kind of a bad thing if we're trying to increase or decrease the value of our function. But it can also be a very good thing if we're trying to find the places where that function reaches its maximum value or its minimum value. In our next class, we're going to call those the critical points of a function of several variables. And then we'll use some strategies to be able to classify which critical points are local maximums, which critical points are local minimums, which critical points are saddles, like in this example. And we can tell it's a saddle because from this point, there's kind of two different independent directions of greatest increase, east and west, and two independent directions of greatest decrease that are north and south. And since we can't have a single gradient vector that points in both directions of greatest increase, the gradient vector's got to be 0 there.